All right, so what happens in Euclidean geometry and any high school geometry course is that we investigate two-dimensional shapes, right? We've done a lot of this with triangles, but kind of the idea is that we have this kind of overarching group of objects called polygons, okay? And then we have some subgroups. One of those subgroups is triangles, right? And then, and this is a kind of a flow chart that says a triangle is a polygon, but a polygon is not necessarily a triangle. Does that make sense? Because a polygon could be a quadrilateral or could be a hexagon or whatever, right? So these arrows are more like going in that direction. That's stupid. Going in that direction. Okay. Every triangle you ever come across is a polygon, right? Okay. And then for triangles, we have subgroups. Okay. Maybe we have acute. Maybe we have right. Maybe we have obtuse. That's a grouping of triangles, right? And then we can have scalene. We can have isosceles. Equilateral. Okay. Now, when we have those things, there's also kind of a flow chart that exists with those. Every acute triangle is a triangle. Every right triangle is a triangle. Every obtuse triangle is a triangle, right? Isosceles triangles can be acute. They can be right. And they can be obtuse. Okay. Equilateral triangles can be acute, can't they? They have to be, aren't they all 60 degrees? Can an equilateral triangle be right? Can it be obtuse? So there should be no arrow going to that, right? Scalene can be acute. It can be right. And it can be obtuse. Okay? And then we've got other things that we could do. There's other types of triangles that we've talked about. And we could create really a nasty kind of web of links between these types of triangles, right? I'm never going to ask you to do other triangles. That's really hard to do with triangles. But what we're doing today, I will ask you to do. Because today, we're talking about another type of polygon. Today, the foundational or initial polygon is a quadrilateral. Okay? That's a four-sided figure, right? Okay? So every quadrilateral, the way we read this, every quadrilateral is a polygon. Is any quadrilateral a triangle? No, there's no links that go over there to the triangles, right? In the first quadrilateral that we investigate is called a parallelogram. And most of this chapter, guys, is about quadrilaterals. We've got parallelograms. We will have some other things here. Okay, trapezoids is one. We will talk about rhombuses, but that's the placement of that is going to be important. We'll talk about kites. Okay, now here's the thing. The way I've written this and drawn this, is any trapezoid a kite? No. Is any kite a parallelogram? No. Is every kite a polygon?
Yes.
Yeah, because I can go through the chart back to it, right? Okay. So you were saying things like rhombus and square and rectangle, right? Those are things that are going to branch off from parallelograms. Okay? And a lot of this chapter is dealing with, I think 3 or 4 sections, deals with parallelograms and the subgroups of parallelograms. And then there's a section or two that deals with trapezoids and then kites. Okay? So we're investigating this quadrilateral collection of figures. Does that make sense to everyone? Okay. Then what we can do is say, okay, we've dealt with triangles. We've dealt with quadrilaterals. What's the next type of figure? We got 3 sides, 4 sides, and then, yeah. We go 5 sides. And then we go 6 sides, 7 sides, 8 sides, right? But what's nice is what we learn about pentagons and hexagons is usually pretty pattern-oriented for what we can learn about heptagons and octagons and nonagons and decagons. We don't need to go really much further than pentagons, what we're going to talk about. Okay? And usually in this class, when we deal with pentagons and octagons and that kind of stuff, we're going to be interested in basically finding their areas, and that won't happen for a couple more chapters. But this chapter is devoted to quadrilaterals. Today's stuff is devoted to parallelograms. Okay? Now, over there on the left-hand side, I got some pictures of parallelograms. First one is a rectangle, right? Okay? It is a parallel. You are right. It is a parallelogram, but a rectangle is a type of parallelogram. The second one is a square, right? A square is a type of parallelogram. The third one, probably a rhombus. The last two are probably rhombuses. Okay? They're types of parallelograms. Okay? When I say you have a parallelogram in front of you, and I don't give you any other special requirements, you don't really want to think about any one of those shapes. Okay? What you want to think about is something that kind of looks like one of those. Okay? Not square, not rectangular, not rhomboidal. Okay? Just parallelogram in nature. Okay? And it won't be until we learn some additional facts about your parallelogram that you can take that thing in front of you and adjust it to a square or adjust it to a rectangle. And that's kind of what, obviously, the next couple sections are about. So let's define what a parallelogram is. Parallelogram is a quadrilateral. Quadrilateral means a four-sided figure with both pairs of opposite sides parallel. Okay? This is not something we can prove. This is something as a society, as a math society, we have decided this is what we're going to call this thing. We've defined it this way. Okay? We're going to categorize these types of shapes as parallelograms. All right? Now, parallelogram is kind of a long word to write, correct? Okay? If I had triangle ABC, we put the triangle out front, and then ABC, right? We read that triangle ABC. Well, if I got a quadrilateral, how many vertices do I need for a quadrilateral? 4. So I'm going to go ABCD. And now out front, what we do is we draw that little parallelogram shape, and that is enough to say I've got parallelogram ABCD. Is that doable? Okay. I'm just kind of lazy. I hate writing the word parallelogram. I don't know why. And we write it a lot in some of the proofs that we're going to do. So when I see parallelogram, every once in a while, I'll write it this way. It means parallel, right? And then I write gram. Okay. Missing an O in there, so if you want to put O-gram in there, you can, but I just don't, inside your proofs, you guys don't want to write that word out all the time. Okay, so shorten it up. All right, so opposite sides are parallel. What's nice about that, if you think about parallel lines, you guys know a lot about parallel lines, don't you? A whole chapter devoted to them. Alternate interior angles, alternate exterior angles, same side interior angles, corresponding angles. It opens the door to all of those facts inside this shape. Okay? And what we talked about last week when we took a quadrilateral and we drew a diagonal in it, that diagonal took your quadrilateral and broke it up into a bunch of what? Well, not a bunch, you just gave us 2 in a quadrilateral. Draw a diagonal in a quadrilateral, you get a, no, you get a set of triangles, right? If I draw, just using this picture here, if I draw that diagonal, I get 2 triangles, right? So you know a lot about parallel lines, you know a lot about triangles. Those 2 ideas or those 2 bundles of information kind of intertwined are going to allow you to learn a lot about parallelograms. Okay? So the first fact that we learned, first theorem, is that opposite sides of a parallelogram are congruent. Opposite sides of a parallelogram are congruent. We'll probably use GeoGebra quite a bit, kind of together throughout this chapter, because what happens is we get a lot of properties, and I don't want to prove every property, because that can be tedious. I want to prove a handful of them, but I also want you to, kind of visually be convinced that these facts are true for every parallelogram. So GeoGebra is a way of allowing us to do that. And it's really easy, actually, to create a parallelogram inside GeoGebra. So we're going to do that. But this first one, I want to prove using a T-chart, using a 2-column proof here. So opposite sides of a parallelogram are congruent. So that's the theorem. So what we're going to do, we know we have a parallelogram. So our if part says, if you have a parallelogram. The then part says, then opposite sides are parallel. Or sorry, opposite sides are congruent. Sorry, that's that. If you have a parallelogram, then opposite sides are congruent. That's what that last theorem says. Well, taking that information and trying to be explicit with one general parallelogram is I start with parallelogram EFGH. So that matches my if part. If you have a parallelogram, then, now your proof part is your then part. So then opposite sides are those opposite sides, EF and HG, and are FG and EH opposite sides. Okay, so we start off with if you have a parallelogram, then opposite sides are congruent, and we then take that if-then statement and just kind of write it for a specific example. Okay, E, F, G, and H is that parallelogram, so then we can discuss some parts and procedures. Okay, now parallelogram is a vocabulary word, right? So when you see that vocabulary, now it's not written out in words, but this says parallelogram EFGH. So what I want you guys to do is write out, let me see here, I want to, all right, so step one, EFGH is a parallelogram. And that's given, right? Okay, step two, I'm gonna do this for you. I want you to construct EG. That would be considered a diagonal. And if you remember seeing that phrase before? Auxiliary lines. We always have the ability, if it's going to be beneficial, to add in any line that we want to connecting 2 points. So go ahead and do that. Now, the reason I'm doing this is because, and providing those, is that if I just think about trying to prove the first theorem of this material, first theorem about parallelograms, you know nothing about parallelograms. You don't know a single thing other than opposite sides of parallel. Okay? If I want to start proving something about parallelograms, I'm going to use that fact that opposite sides are parallel, so we'll write that down here in a moment. But then I've exhausted everything I know about parallelograms, right? So what I have to do, if I've exhausted everything I know about parallelograms, is I have to start being able to maybe use other shapes that I know stuff about. Well, the only way I can develop other shapes that I know stuff about is to draw that diagonal. Once I draw that diagonal, now it opens the door to triangles, right? We know a lot about triangles. So it allows the ball to kind of keep rolling with our proof if we draw in that auxiliary line. So what I want you guys to do, first thing, because this is a parallelogram, I want to write down which sides are parallel. So we're going to say EF is parallel to HG, and HE is parallel to FG. Definition of parallelogram. All right, we draw that in our picture. Now here's the nice thing. Every single time, this is kind of a pattern, but every single time that you see the word parallel in a proof, you want to start thinking transversals and start thinking alternate interior, alternate exterior, same side interior, corresponding angles. Start thinking about those things. Okay? So that's really all we have, right? We create the word, we develop the word parallelogram. That's vocabulary. Gives us some information. And that information is what we see in step 3. And inside step 3, there's other words. There's the word parallel. It's a vocabulary word. And if you remember back to proofs in chapter 3 when we dealt with parallel lines, we developed that word parallel. We started talking about alternate interior, exterior angles, same side interior, or corresponding. So let's look at this. Let's say that I focus on one set of parallel lines. Let's look at that set there, top and bottom. And then I look at that thing right there. Is that blue line a transversal? What would that tell you then about maybe that blue angle and that blue angle. They're the same. Why? Alternate interior. So let's write that. Let's say angle FEG, angle FEG, congruent to angle HGE, and that is the alternate interior angles theorem. Said if two parallel lines are cut by a transversal, then alternate interior angles are congruent. Does that make sense? Oh, I missed the G. Thank you. All right. Is that okay with everybody? All right, so that's nice. But what about doing something like this? This was F. This was H. Can I also look at that parallel line and that parallel line? Is the blue line still a transversal for those two? Okay, so I erased that on accident. So now we could say that this green angle is congruent to that green angle, couldn't we? Because again, they're alternate interior angles. So I'm going to write HE and angle HEG is congruent to angle FGE. And the reason for that is alternate interior angles again. Is that doable for everybody? Okay. So I'm just going to clean the picture up real quick. What we've just figured out is that that angle is congruent to that one to that one, right? You have two angles of one triangle congruent to two angles of another triangle. And we have triangles in our picture. We usually try to prove those triangles congruent, right? Do we know that EG is congruent to EG? That's the reflexive property, right? So now that I have the reflexive property going on, you have three parts of this top triangle congruent to three parts of this bottom triangle, right? What's that tell you about those two triangles? Does it tell you that triangle, let's go FEG is congruent to triangle. If I go F to E to G, I'm going to go H to G to E. That makes sense, everyone? F to E was from no marks to 2 marks. So you're going to go from no marks H to 2 marks G. You guys remember the reason why? Why did that? G doesn't want to stick. F, E, G. That needs to be, it's H, G, E, right? F to E to G. So yeah, H to G to E. All right. What's the order of the parts here? You got an angle, and then a side, and then an angle. So that's angle, side, angle. All right, so what we learn about parallelograms is because of what we know about triangles, right? That's the only reason we know information about these figures. Now, what we're trying to prove is that EF is the same thing as HG, right? Well, as EF, first two letters there, and HG, first two letters there. So I'm going to write EF is congruent to HG. And the other thing was that FG, first letter and last letter, is congruent to EH. Or this first letter, last letter? Okay, so FG is congruent to EH. And what's that reason? If I show the triangle is congruent, then I want to say that the rest of the parts are congruent. CPCTC. Good, Gage. So now we've proven that fact, that theorem, that said opposite sides of a parallelogram are congruent, basically by using triangles, right? Okay. Now, just humor me here real quick. Let me clean some stuff out in this picture. If you know that those two triangles are congruent, what's that tell you maybe about angles H and F? What do you think you'd make the argument about H and F? They're equal, yeah. H is the first letter there, right? F is the first letter here, right? How would you, just give me a word for the parallelogram. So let's get rid of this line here. What would be a word that maybe you could use that would reference H and F together as a group? What kind of angle would you call it? Adjacent means next to. So what would be kind of the opposite of next to? And I just said it when I said the opposite of next to. Opposite, right? Would you consider H and F the opposite angles of that parallelogram? So can you convince yourself that maybe we have a theorem that also says opposite angles of a parallelogram are congruent? Does that make sense to everybody? And what's nice about that, what's neat about that, is it's the exact same proof we just did, except for the last statement. There's angle H, there's angle F by CPCTC. Okay? Now there is one thing that we got to pay attention to when we want to do this. We want to prove opposite angles congruent. Let me get this thing, there you go. Because when I draw this diagonal, that sucked. When I draw that diagonal, a little bit better. That angle and that angle are the only one that we can talk about as being congruent by CPCTC. We also end up finding out eventually that that angle there and that angle there are also opposite angles from our parallelogram, aren't they? So the way that I would go about trying to prove that those two things are congruent is that I draw that diagonal. And do you think I could probably go through and prove those two triangles congruent? And then by CPCTC, I could say that angle E and G are also congruent. Okay? So what happens, and the reason I wanted to do that proof is to kind of open your eyes to the fact that when you're dealing with parallelograms, if you understand parallel lines, you understand triangles, you should have a pretty good foundation in being able to understand, recognize these theorems, and hopefully apply them and use them. A couple other theorems. It says diagonals of a parallelogram bisect each other. Diagonals of a parallelogram bisect each other. It's kind of nice. We can prove that. It's a little bit of a longer proof. So what I've done with GeoGebra here is I just create a bunch of parallel lines and some points here. Not all these points are necessary, but that is that red shape is a parallelogram. If we wanted to look at, that slope is 0.52, that slope is 0.52, so they're parallel. Negative 0.34, negative 0.34, so they're parallel. Is everybody okay with that? So we got a parallelogram, and the way I set this up is I can move these things around, and you're going to see that those slopes still end up being the same for opposite sides. So that is definitely a parallelogram. But I asked it to come up with the diagonals. Okay, see if I can. There we go. So D to H is one diagonal, and then F to E is another diagonal. And when they intersect, they create this point I. But I asked GeoGebra to go ahead and find the lengths from D to I and then from I to H. And what do you notice about those two lengths for that parallelogram right there? They're what to one another? Guys, DI and IH, how do they relate to one another? They're the same, right? What about FI to IE? They're the same. So did both diagonals get cut in half? Yeah, and that exists no matter what triangle parallelogram I look at. Okay, that one's a completely different one. Do you still get the same relationships? Diagonals are getting cut in half. Both of them are getting cut in half. Now, I just want to kind of maybe open your eyes to some things that we'll see later on. Let's say that I was able to do this in the last class easy, but maybe not. Huh? They're just dots on lines that I had to use to create the parallelogram. What kind of parallelogram do you think that is?
Square.
That may be.
Probably rectangle.
Most definitely a rectangle, right? Now we're going to find some distances to see if it is a square or not. I don't think it is. But what do you recognize about all four parts of those diagonals?
They're all the same.
They're all the same. So what's that tell you about the original two diagonals of a rectangle?
They're the same.
Yeah, they're the same. One diagonal is 10.04 and the other one's 10.04, right? Is that true for a general parallelogram? Is that true for that parallelogram? Are the diagonals of, you got one diagonal being 10.04, and you got the other one being 6.58? So diagonals for a parallelogram in general are not the same, right? But for a rectangle, they are. And that's what makes a rectangle a special parallelogram. Does that make sense? There's special properties, okay, that exist that allow you to move from just a general parallelogram to either a rectangle or to a square or to a rhombus. And that's kind of what we'll investigate as we move forward in the next couple days. What if I did this? I'm just going to clean those out and then put in that line, and that line. What would you tell me? What do you think? Oh, wrong order. There we go. What do you think those two angles are going to add up to?
180.
Why?
Because they're same side interior.
Good. Okay. If I get rid of that object there, okay, those two angles I just highlighted were same side interior angles for the top and bottom parallel lines of your parallelogram, right? Okay. Now, in a parallelogram, we have a special set of words for those types of angles because if I go back and look at what do you think you know about those two angles? Same side interior again, but they're a different set, right? Because they're a different set of parallel lines. Okay? So those types of angles, the ones that come right after one another, what's a word that we use in math for things that come right after one another? Consecutive. Good. Okay? So we get this last theorem that says consecutive angles in a parallelogram are supplementary. So you're going to be able to collectively look at a bunch of different groupings of angles and add them together so they equal 180. Okay? People get confused, okay, because you've got two properties that deal with angles. One says opposite angles are what?
Opposite.
Congruent, right? And they look congruent, don't they? I'm going to tell you in a parallel, if you got parallelogram, you know you got parallelogram, you can go off the looks for their angles, for their relationship. You know those things look congruent, so opposite angles are congruent. Consecutive angles, again, go off the looks, okay? They look like they're going to add together to give you 180, right? Could you take, like say I gave you this parallelogram in a piece of paper, as a piece of paper. Could you tear that corner off, put it over here, and attach that corner right there? And does that then give you that straight line, 180 degrees? Okay. So, use those properties, those visuals to help you. There is an assignment, 6.2, in Math Excel. You should be able to move through it pretty quickly, I would think. Not extremely difficult, but my concern, and it happens every year, is that you say, these things are easy. This is a piece of cake. Or maybe you just don't care and don't take the time to learn these effectively, okay, and learn them really well. Because what happens when we talk about squares, there's going to be 4 or 5 properties about squares that make them different than normal parallelograms. 4 or 5 properties about other shapes that make them special. So at the end of the chapter, you're going to have all these different properties. And you got to know which properties fit for which shapes. All right? If you don't learn them early on, you're cramming at the end before the chapter to learn a very large amount of properties, a very large number of shapes, and which properties go to which shapes. And that's really hard to do. But if you learn it as we go, and you convince yourself, and you're really comfortable as we go, it usually isn't an issue for people. This ends up being one of the harder tests for some reason in this course. Okay, I think people collectively over the years think this test is a little bit harder than the last one. Okay? Because of the amount of properties and the amount of logic that you have to use on that test. Okay? You may go to lunch.
See you, Mr. Beck.